Welcome to our Quantum Deep Dive.
Great to be here.
Today we're plunging into a truly fascinating concept, one that pulls together the bizarre world of quantum physics and the cutting edge of artificial intelligence.
Yeah, it's pretty wild stuff.
We're getting into an essay titled Quantenwort Einbettungen NLP mit Quantenpower by Jürgen Schneppert.
That's right. And our mission today really is to explore how these strange, frankly wonderful rules of quantum mechanics might just revolutionize how machines understand human language.
Okay.
Specifically through something called quantum word embeddings. You can think of this as your shortcut, maybe, to understanding a pretty groundbreaking intersection of AI and, well, the very fabric of reality.
Sounds big. And to set the stage, we'll first unpack why the traditional ways we do natural language processing, NLP, why they're hitting some very real walls.
Exactly. What are the limitations?
Then we'll see how these quantum principles usually kept for the subatomic world could offer surprising, maybe even powerful new solutions for something as complex and fluid as our everyday language.
Yeah, it's quite a leap.
Okay, let's dive in then. Before we get to the quantum magic, tell me, what's the big deal with how AI currently understands words? What are the sticking points?
Right. So historically, classical NLP models, they've largely relied on what we call word embeddings.
Embeddings, okay.
Yeah. Imagine taking every word and turning it into a mathematical vector, basically, a unique list of numbers. Tools like Word2Vec or Glove do this. By analyzing a word's context across massive amounts of text. The core idea is that, words used in similar ways should have similar numbers, similar vectors.
So it captures meaning through context.
Exactly. It was a huge leap forward, letting computers grasp semantic relationships. But
there are problems.
There are. This approach, despite its successes, faces some pretty significant hurdles. The first, and maybe the easiest to grasp, is word ambiguity. The essay calls it Mehrdeutigkeit.
Right, words meaning different things.
Precisely. Think of bank, financial institution, riverbank, and airplane turning. Classical models, with their fixed vectors, one number list per word, they often struggle badly with this nuance. They might give bank one sort of average meaning.
Which doesn't always work.
Not when context is key. Now, newer models like BERT, they try to adapt contextually, but they are computationally heavy, very expensive, and they still don't perfectly solve it.
So it's like the AI knows the dictionary definition, maybe, but not which one applies right now. It misses the vibe, the specific meaning in the sentence.
That's a good way to put it. It knows the word, but maybe not its intent in that moment.
Okay. What else?
The second big challenge is that semantic relations are often deeply nonlinear.
Nonlinear meaning?
It's not simple A plus B equals C. Complex relationships, synonyms that aren't quite the same, antonyms, metaphors, sarcasm especially.
Yeah, sarcasm is tough for AI.
Incredibly difficult to represent with simple linear math. Language is just too rich, too nuanced for straightforward equations, meaning interacts in complex ways.
Got it.
Then there are the notorious scaling problems. Modern deep neural networks, especially those big transformer models like BERT and GPT.
The one that everyone talks about.
Yeah, they power so much today, but they demand astronomical computing power, huge resources.
Training them takes ages, right?
Weeks, sometimes, on specialized hardware. Consumes massive energy, billions of parameters. It makes them incredibly difficult and expensive to scale up. Honestly, it feels unsustainable long term.
Wow. Okay. That's a big one.
And finally, a huge one, especially for important stuff, is the lack of interpretability. The black box problem.
Meaning we don't know how they decide things.
Exactly. They get impressive results, sure, but they operate in such complex ways it's incredibly hard to understand how they arrive at their conclusions. Imagine using one for medical diagnosis.
Right.
It might say tumor present, but it can't explain why. What features did it look at? For medicine, law, finance, not knowing why is a major barrier to trust. It's like having a brilliant oracle that can't speak.
So it's not just about throwing more data or power at it. We're hitting some fundamental limits in representing meaning itself, like the AI gets the letters, maybe the words, but not the music they make together.
That's a great analogy.
And this is where it gets really interesting.
Yeah.
This is where quantum principles come in.
Indeed. The essay highlights 3 core quantum mechanical principles as potential solutions. First up, superposition.
Okay, superposition.
In the quantum world, a system isn't just in state A or state B. It can be in multiple states at the same time until you look at it.
Like Schrodinger's cat. Sort of. Both alive and dead.
Kind of like that, yeah. Think of it like a dimmer switch for meanings. A word isn't just on for one meaning, but maybe partially on for several meanings at once.
Okay. How does that help with language?
Well, take our word bank again. In a quantum model, bank wouldn't be just one fixed meaning. It could exist in a superposition of meanings: financial, river, tilting all simultaneously.
All possibilities alive at once.
Exactly. Holding all its potential, waiting for context to clarify. Just like a quantum particle holds potential states, a single quantum word can inherently encode its ambiguity.
That makes so much sense. It's like the word is primed with all its meanings, ready for context to pick the right one.
Precisely. Next up, entanglement.
Ah, the really spooky one.
Yeah. Spooky action at a distance, as Einstein called it. This is where two or more quantum particles get linked. Their fates are intertwined no matter how far apart they are.
Like if you measure one, you instantly know something about the other.
That's the idea, like two perfectly coordinated dancers. For language, entanglement could represent deep, non-trivial semantic links between words that classical methods just can't capture well.
How so?
Instead of simple linear connections, it could model complex dependencies, like raining cats and dogs.
Okay.
The words cats and dogs here aren't just individual concepts. Their meaning is deeply entangled to mean heavy downpour. It allows for a holistic understanding where the whole is more than the sum of its parts.
So if raining cats and dogs were a quantum phrase, the words become linked, fundamentally, to create that specific meaning. That's powerful, goes way beyond individual definitions.
Exactly. They become a single semantic unit. Which brings us to the third principle, quantum measurement.
Measurement, like observing the particle.
Right. The act of observing a quantum state forces it to collapse from its superposition of possibilities into one single definite state, like a spinning coin landing heads or tails.
Okay.
For NLP, the meaning of a word becomes concrete only when it's measured by its surrounding context in a sentence.
Ah, context is the measurement.
You got it. Before context, bank is in superposition. Add river, and that context measures it, forcing it to collapse into the riverbank, meaning it mirrors how we humans resolve ambiguity instantly.
Okay, wow. So superposition holds the possibilities, entanglement links related concepts deeply, and measurement uses context to pick the right meaning. What does this mean for actually building these things? How do you get quantum word embeddings?
Good question. It changes how we even think about representing words. Instead of fixed numerical vectors in, standard mathematical spaces.
Listen to numbers.
Right. Words are represented as states within complex Hilbert spaces.
Hilbert spaces.
Yeah.
Sounds complicated.
It is, mathematically, but think of it conceptually. A classical embedding is like a single dot on a flat map. A Hilbert space is like a vast multidimensional landscape. A word isn't one static dot, but a fluid combination of many potential states, allows for all that overlaying of meaning, a much richer canvas.
Okay, a richer space for meaning and context. How does that work?
So for context-dependent meanings, context isn't just tweaking a vector slightly. It acts as a projection mechanism, a measurement.
The measurement again.
Yeah. If bank is holding both financial and river possibilities, the surrounding words act like a spotlight, or maybe a filter. This spotlight forces the meaning to collapse into the one relevant for that specific sentence. Meaning becomes adaptive, fluid, not static.
It feels much more like how language actually works.
It does, doesn't it? And finally, there's a difference in quantum probabilities versus classical probabilities.
How they calculate likelihood?
Sort of. Classical AI, like neural nets using softmax, often weigh options exponentially. Quantum models derive probabilities differently, from squared amplitudes after measurement. The key thing is, quantum methods inherently allow for more dynamic calculation and naturally fold context in, rather than layering it on top.
More intuitive, maybe.
Potentially more intuitive, and perhaps more accurate for how meaning gets resolved.
This sounds incredibly powerful. More nuance, context aware. But how do these quantum word embeddings actually stack up against the best we have now? Like those huge transformer models. Where's the trade-off?
That's the million-dollar question, isn't it? And the essay gives a balanced view. Let's break it down. First, semantic accuracy and context sensitivity.
How will they understand meaning?
Right. Classical models, even the fancy contextual ones, struggle with ambiguity. Polysemous words, idioms, they often get tripped up.
Like bank.
It's like bank. The quantum potential here is huge. Better ambiguity resolution is built in because words start in superposition and collapse based on context. An entanglement. Great for modeling complex relations, sarcasm, metaphors.
So AI might finally get my sarcastic emails.
Aha! Maybe someday. That's the potential.
Okay, potential is high for accuracy. What about efficiency?
Computational effort and efficiency. This is where it gets tricky. Classical models, those big transformers, need immense power, run on GPU STPUs, cost a fortune to train. That's their downside.
Right.
Now, for quantum, simulating the stuff on classical computers is incredibly expensive. Exponential memory needed for large texts. It's just not feasible right now for big tasks.
And actual quantum computers.
Still very limited. Few stable qubits, high error rates, they lose their quantum magic, decoherence really fast. It's early days for the hardware.
So the potential is there, but the hardware isn't quite ready for prime time. That's the bottleneck.
Exactly. The promise is that if we get powerful, stable quantum computers, they could offer exponential speedups. Superposition allows massive parallel processing. But that's a big if for now.
Okay. What about understanding how they work? Interpretability.
Right, the third point. Interpretability and explainability. This is a weakness for classical deep learning. The black box problem. Billions of parameters. It's almost impossible to trace how a decision was made.
Which is bad for trust.
Very bad. Now, quantum models, theoretically, offer a strength here. Their structure is based on explicit math, Hilbert spaces. It allows for more transparent, traceable relationships. How context leads to meaning via measurement is, in principle, an explicable process.
So you could actually follow the reasoning.
Potentially, yes. Instead of just getting the answer, you might see the steps. That's revolutionary for critical applications where you need to know why.
So huge potential for accuracy and interpretability, but major hurdles with hardware and current simulation costs.
Yeah.
It's compelling, though. Not just getting the right answer, but understanding it. Given that, where might we see quantum word embeddings make the biggest splash eventually?
Well, the essay points to several exciting areas. Machine translation is a big one.
Going beyond word for word.
Exactly. Grasping ambiguity properly. Entanglement could help transfer meaning, including idioms and cultural nuance, much more accurately between languages. Fewer awkward translations, hopefully.
That'd be nice.
Then, sentiment analysis. Capturing subtle things like irony or sarcasm using superposition. Mapping opinions in a complex way. Understanding the real vibe of a text, not just keywords. Think customer feedback, social media.
Getting the nuance.
Right. And semantic search and knowledge representation. Imagine search engines that understand what you mean, not just the words you typed. Quantum models could consider multiple meanings, adapt to context in real time, maybe build quantum knowledge graphs that are way smarter.
A search engine that gets me. Yeah.
That's the dream. But again, we have to be realistic about the challenges.
The hardware?
Hardware limitations are still number one. Qubit count, stability, error rates, decoherence. It's a massive engineering challenge.
And the software.
Algorithmic development. We need new quantum algorithms specifically for NLP. It's a whole new field. The rule book is still being written.
So what's likely in the near future?
Probably hybrid models, combining the best of both worlds. Use classical NLP for the heavy lifting, maybe initial processing, and then bring in quantum-inspired techniques for the really tricky semantic parts where nuance is crucial.
Leveraging strengths from both. Makes sense.
It seems the most practical path forward for now.
It really feels like we're standing at the edge of something new, doesn't it? Applying quantum physics to language. It's kind of mind-bending. It really challenges how we think about information.
It absolutely does. And as we've explored, this journey of quantum word embeddings is still just beginning. But the essays suggest, and I think it's right, that with advances in hardware and theory, this could genuinely spark a new era for NLP. Even starting with hybrid systems, the implications are pretty profound.
What's so fascinating, I think, is this core idea that the universe's most fundamental rules, the quantum rules for the very small, could radically change how we interact with information at the human scale, how AI understands us, our language. It's a wild thought that superposition and entanglement might unlock a deeper AI understanding of communication. Maybe it will finally get my emails.
Indeed. The potential to transform how machines process and understand language and therefore our digital world is truly immense, even if the path there is still being built.
Well, that wraps up our deep dive into Quantum Word Embeddings NLP mit Quantenpower by Jürgen Schneppert. Really fascinating stuff. If you're as intrigued as we are and want to explore more of his work, you can find it at schneppert.de.
Definitely worth checking out.
Thank you for joining us on this exploration, and we look forward to our next deep dive with you.